We're back. The next thing I wanted to cover is something called coincidence dip. This is a region of frequencies where the transmission loss is controlled by stiffness and damping. This will apply to these single leaf partitions, and then when we get to the double leaf, it'll apply to each of the leaves in that case. So this is a useful concept to be aware of and to be able to identify and be able to calculate where it happens. So this is most pronounced at the critical frequency. This is a resonance frequency. That resonance occurs where the wavelength of the free bending waves in the panel coincides with the wavelength of that sound in the air that's incident on it. We calculate that with this equation here. We have the speed of sound in air squared over 1.8 times the partition thickness. And then we have the partition material density over the Young's modulus, and we take the square root of that. So that gives us the frequency in hertz. It could also be, so this table is not from the book, it's from a different resource, but here for common building materials. So not only architectural, but say enclosures, some say like a mechanical system. Lead isn't so common anymore. There used to be a lot of lead impregnated things because it's so dense. It does a really good job for, it's dense and it's relatively limp, so it did a great job for isolating sound, but it obviously has toxicity issues. But if you have any of these materials, you know the thickness of your material, you can just come and use this table and get the critical frequency. So this is what the critical frequency does to the transmission loss. So here there's R with 0 in parentheses after it. That is the normal transmission loss. And that first equation we had would give you this line. And then if we go back, so let me first start with this. So we see this drop. I think that's around 6 decibels, but this would be the difference between the normal incidence and the diffuse field incidence. So that would be, say this equation, 47, or I didn't point this out before, but some books have 48 in here. So 48 or 47, and then this one is 42. So it's 5 to 6 decibel difference depending on which publication. That's the drop between the normal and the field incidence. Those track along pretty closely up until you get to this coincidence dip. So this is where, so right here at 0, that's where that coincidence dip is going to occur. And you're gonna get this fall in transmission loss or sound reduction. And then it's gonna pick up again for this, this region of frequencies greater than the critical frequency. And at this point, when this equals 3, so this would be when the frequency is twice that. You might want to check the calculation, but I think when that's twice that, this would be 3. So we'd be at this point. And then the difference between the normal incidence and the diffuse field incidence is going to be 2 minus 10 log the loss factor. That's what this eta is. We're going to cover that here in a minute. I'll give you some data for common materials for that loss factor. So you can determine that point, and then the slope of this, I believe, is 18 decibels per doubling of octave, but we're going to give you an equation so that you can calculate that. That is this one, so it's going to be that incident sound whoops. So normal incidence transmission loss. Let's 10 log the ratio of the frequency divided by the critical frequency minus 1 plus 10 log the loss factor minus 2. So at that point, right here, we're just looking at this subtracted from that. This is not part of it at that point. So just the variables, I think I said all these as I described that. We have the normal incidence transmission loss, critical frequency, the frequency that we're interested in calculating for, and then the loss factor, which we'll cover on the next slide. That loss factor is the power of a material to convert part of the acoustic energy into heat instead of transferring it as airborne noise. So here we have this table of materials and their properties. The loss, so you might, a lot of these come into play in these equations as we've seen, but here's the loss factor. That one's probably a little more difficult to find than these others. Here it is. Then here is some actual data, some measured data. We have data for a concrete partition, a gypsum board, and a plywood. So here's the mass law, and then the critical frequency for the concrete, I think, is 200 hertz. So right there we see the dip. Then plywood is going to be next. Plywood is 1600, so maybe dip's occurring somewhere right in there. And then gypsum board, 3150, so right in there. We see these dips for all three. So with gypsum board and plywood, see it there, 16 millimeters, a 5/8 inch plywood, and then 13 millimeter 1/2 inch gypsum board. The gypsum board is denser than plywood, and it's not as stiff. So it'd be good if we only had, like, say if they were both 5/8 inch sheets. Like the Type X gypsum board that's meant for it satisfies the fire ratings. That's what's commonly used in walls now. Like the 1/2 inch might be used in just your home walls where you don't need to from room to room, but in other, say like in multifamily projects where you need to meet fire ratings for partitions from one side to the other, the 5/8 inch is common these days. So it would be good to have the same thicknesses so we can compare just what the stiffness and the density, we isolate that variable or those variables, so we're not looking at, you don't have to consider thickness too, then you could see the comparison. But it is good to see that the thinner, stiffer, and lighter weight one occurs sooner than the heavier or the denser, not quite as stiff and thicker one. That's it. I do have, so here we just had part 1A, B, and C. I do have a part 2 as well. So I'll be sending you an email with links to all these.